Today I'd like to talk about a solution we have for addressing one of the issues that comes when we want to make optical measurements on devices that have been made on wafers, including when they're broken down into bars or chips. I'm Mike Kelly from work on Photonic Applications at Keysight. So if we think about what we need to do when we're making measurements on devices that we're making photonic integrated circuits, this is something that we want to increasingly do at production levels of scale, of speeding it up. And so some of the things that come up are, first of all, how do we couple signals in and out of the device before they've been packaged and we have permanent connections to them. So we have to do that with optical coupling, with electrical coupling. And then something that comes up that's kind of unique for the optical versus the electrical is the need to do this at a chosen wavelength, or looking at the dependence on wavelength as well as the dependence on polarization. And polarization turns out to be one of the key issues. That's what I want to address today. Just looking at this, here would be a typical curve over wavelength of what the insertion loss of a device could look like in the one polarization parallel to the plane of the chip versus polarized perpendicular to the wavelength of the chip, of the plane of the chip. So moving on, looking at optical parameters, this is usually dependent on wavelength, and what we're usually looking at is the power that we're running signal into the device. We want to look at how much goes through, potentially how much gets reflected back, and from that calculate insertion loss, return loss, polarization dependent loss as the ratio between the direction where we get the most transmission or the least transmission. And when we go on to integrated devices, that often means that there's also an integrated photodiode or several of them on there. And so instead of having an optical output, we'll have an electrical output, probably photocurrent later that goes through a transimpedance amplifier. And so we want to be able to measure this electrical output for those kind of integrated devices. The basic kind of test we make for these, as well as for packaged instruments, is to sweep a tunable laser over a certain wavelength range. And while we do that, we make synchronized measurements of the output signal, usually with an optical power meter. And we can sweep over a range, say, of 80 nanometers per second, even up to 200 nanometers per second, and sample every picometer if we want to, every 100 picometers if that's enough resolution for us, and produce the kind of curves like we were just looking at. But now if we look at polarization, we've got the issue that, so light being an electromagnetic wave has the electromagnetic field in a certain plane, and that's that orientation of that plane is what we refer to as polarization. A lot of times when we're talking about this, we show it on a representation known as the Poincare sphere, where we would have linear horizontal polarization at one place on the equator. Vertical would be on the other side of the sphere. Diagonally would be the two east and west points, if you like, and the north and south poles. Those are circular or right circular or left circular polarization. That happens when you have a component in a fast axis and a slow axis of the device, and it causes the phase to be offset between the two directions of polarization. The thing is, when we go into a fiber, we can go in with one known state of polarization, but we don't know what's going to come out on the other side. It can look like that. That's because the polarization changes through the fiber. There's not a well-defined axis. Usually we don't have any problem with that. Usually that's to our advantage, but it's difficult now when we want to make a measurement in a certain state of polarization. One way we can do that is using polarization maintaining fiber. That's a special fiber with stress elements built into the fiber around the core of the fiber, and that gives a different index of refraction to the fast axis versus the slow axis. And in that way, it's possible to send a certain defined state of polarization through the fiber, and we'll always get that out at the other side. But we don't have flexibility over choosing different states of polarization. We'll always get either the one or the other. And if we try to couple in diagonally, say, we're going to get something that changes very rapidly with temperature and with wavelengths. So that's not a useful mode for measurements. So going on to this, if we look at a device under test, there's a couple ways to look at to measure the polarization dependence. The simplest way is just to use a polarized light source and use a polarization controller that scrambles through a lot of states, potentially randomly, and we just measure the maximum power and the minimum power, or the maximum photocurrent and minimum photocurrent, and from the ratio of that we can get the polarization dependence. That's fine if we could only need a measurement at one or a few wavelengths, but very slow if we have to do that thousands of times, like we would if we wanted, say, 10 picometer resolution across a spectral range. And so we use a different approach. Where this is, however, very useful is when we want to measure something with very high polarization extinction, because then you really need to make some measurements very close to the minimum of the signal. And we do have a way to support that in our software for adding that in addition to this method, which makes swept measurements. Now we can take this polarized source and sweep with a certain state of polarization and then measure how much power goes through that, then do the same thing at a different state of polarization and a different. With 4 states, we have enough information to make a matrix calculation and determine the maximum and minimum without ever having had to reach that state of polarization. That turns out to be very useful. That's a state-of-the-art technique for the industry. And at Keysight, we've implemented an advanced form of this where instead of making 4 sweeps at 4 different states of polarization, we use a fast-switching polarization controller like you see here with the laser and with the power meter. And because this polarization controller can make a repeatable set of polarization states very quickly, we can do this while the laser is sweeping. So we make 1 sweep. During that time, we switch through 6 states of polarization in about 300 microseconds. So we're very stable against any kind of temperature drift or vibration because the whole measurement is made in less than a millisecond for the polarization dependence. And that again gives us the Mueller matrix that we use for calculating polarization dependence. And we can also use that to analyze for what does the spectrum look like in the 2 main axes and without having to go through the effort of making that alignment. And that's what turns out to be very useful now when we do wafer measurements. Here's a simple example looking at a bandpass filter this way. On the top you see the average insertion loss. On the bottom you see the polarization dependence, and it's got kind of a characteristic V shape that drops down to 0. And what's happening there is, if you look at the TETM analysis, we've basically got, for the one polarization, the center wavelength is shifted a little bit compared to the other polarization. And so on the one side, one of them is higher, on the other side, the other is higher. They cross, and at that crossing, we have 0 polarization dependence. But the interesting part here is to be able to separate and not just get the top curve and the bottom curve, but get this central one that shows what the curve looks like for a certain state of polarization. Before we go more on the wavelength, we do the same thing with integrated detectors. Here, for instance, is a device used for LR4 receivers where we separate 4 wavelengths to 4 detectors. And what we're going to do with a setup is, instead of using an optical power meter, you can see the source measure unit, the B2900, outlined in green there, and that can measure the photocurrent. And we get the same kind of measurement curves like you see here. So this is now looking at responsivity of that device for the 4 channels with the 4 detectors. And the 2 curves, dotted and solid, are showing the polarization state where it has the best responsivity and the polarization state where it's lower. So now back to looking at wafers again. We can be coupling light into that on a wafer by using a surface grating arrangement, a special structure written onto the, or structured onto the wafer device so that light coupled in from the top of the wafer is turned into the plane and moves into the waveguides. Or if we're already a chip, we can couple into the edge of the device. In each of these cases, we usually are interested in a particular state of polarization. And so a typical way of doing that has been, especially in development, maybe just to use a manual flipper kind of polarization controller to turn the polarization until you get it into that state. The problem with that comes up is what that polarization controller does at one wavelength won't be the same at other wavelengths. So if we try to sweep now the wavelength range, we might be good at the starting wavelength, but then it drifts away from the ideal state of polarization, and so we don't get a clean measurement. And this dependence of the state of polarization on wavelength or even on time is just a basic feature of using single mode fiber going from our instruments to the probe. So instead of that, if we do this matrix method with a single sweep, we can just make the measurement without trying to align the polarization, and afterwards calculate that polarization. And in this case, we get a curve that's showing us the characteristics of the device itself the way we want to see them. And we get that in 10 seconds, say, very quickly, without having to go through this manual or automatic search procedure for polarization. So this is the device like we have on the booth, which actually has an interferometer in there. There's places where we have high interference, low interference. This is about 20 picometers between these peaks. So you can imagine if we were trying to sit on one of those peaks and maximize the signal, that's going to be really sensitive to, and we're not going to get a nice flat curve across wavelength either. But now if we make the measurement, we do get that. We get something that looks flat across wavelength. We get the whole thing without having to tune up. And we've got you can see that there are places actually where the polarization state in the one axis crosses the one below, but we can sort that out as well with our software. This is another picture of what that whole measurement looks like. We can measure that over, say, the whole C-band. That just looks like a big smudge in a way, because if we zoom in, it's showing these kind of ripples on it. And you can see that in this case, I've done one measurement where I have done it with an aligned PMF fiber coming right out of the tunable laser. In the other case with the measurement. And you can see they overlie each other very, very well. So just to go back to this closing, we've got this set up. We'd be happy to have you stop by and take a look at our demo on the booth, and please feel free to check on at this link where we have more details on the software that we use to support this solution. So thank you.